I'm not seeing anything.
Oh, let me see. Okay, hold on 1 second. Sorry, now I'm having difficulties.
Microsoft.
I know, right? Okay, let's see.
Yeah.
Okay, there we go. Now do we see it?
Yes.
Perfect.
Okay, and can everybody see it? And I guess I take that as yes. Okay. All right. Very good. So first of all, thank you so much, Myra, for organizing this. Right. So this is, I guess, very important for all the graduate student and undergraduate student who's interested in doing research, right? Because oftentimes, we're busy working in the lab. You guys don't know what we do other than the class we teach, right? But so we want to show you briefly what we do here, right? So again, my name is Yirong Lin, and then today the presentation is titled Design and Additive Manufacturing of Functional Polymers and Ceramic Composites. And I work in both C-Center and CAC Center, and working on energy, materials, and composites and additive manufacturing. So next slide. Okay. I want to open today's presentation by a brief introduction. I don't know whether we can do full screen of this. No, I guess it's hard. It's I send you the PDF, no, the PowerPoint, because PowerPoint is like 500 megabytes, way too big to send. But this is fine. So I want to open today's presentation by acknowledgement, where I want to show you guys who we are, what we do, and what's our vision and mission, right? So I have a bunch of pictures here. I'll go over one by one with you guys, right? So first, I want to tell you guys, we are the Smart Materials Processing Lab. We call them SMPs, as you see in the lower left, right? So what's our mission is to have student success through research and education in functional materials. And our vision is to pioneer in functional material synthesis and advanced manufacturing. So really, the stuff we do on research sits in materials, manufacturing, and mechanical engineering altogether. So it's a very interdisciplinary group we have. Okay, so let's go over these pictures a little, because this is basically a highlight of what we do, right? So the first picture on the top left you see is a lot of students working in my group. They got a scholarship offered by Honeywell. They were doing some internship working on additive manufacturing of ceramics and polymers. And the second picture is Alexis. He went to Boeing this summer, who also get highlighted, worked on a lot of ceramics additive manufacturing stuff there, right? And the picture on the top, third one here, is Bethany and Liz. They were working at SCM at a CAC Center, looking at this material synthesis later on for additive manufacturing of polymers. And then the picture on the right top is Paulina. She's working with Microsoft. She helped me working a lot on polymer and ceramics printing using bond and some polymer, luckily the sintering work. And a bunch of pictures in the second row is a lot of my student, especially PhD student, Jaime. Jaime, the first picture over here you see, and Luis graduated last spring, and he defended the last day before campus shut down. So we got lucky, right? And Elsa, she's working on printing of V-trimmers, which is a unique polymer, has self-healing properties. And the picture on the right, her name is Mariana. She's doing her PhD now, master in the University of Texas at Austin, right? And then the picture on the right is Jaime, who I just met with this morning. We went to get COVID testing together, and he's also a winner of NSF Graduate Research Fellowship Program, and I'm very proud of him. Right, he went to an intern in Nano this past couple of summer, and then he's working on printing of ceramics, glass, and polymers with us. And the picture on the lower left is a Christmas get-together party of my group and my family, as you see over there, right? So I always say, working in this big group, it's not only about working, right? We're extended family. So you guys are the reason why I do the things I do, right? So I'm very proud of every single one of them. And yeah, very happy to have you in my life. And the picture on the lower row, the second one is we got a project from Lockheed Martin looking at using artificial intelligence and non-destructive evaluation to detect the defects in composites. And lastly, a couple of picture is Sebastian, who's working on ceramics AM stuff. And the last picture to the lower right is all the 3 PhD students working with me, Luis, Jaime, and Annabelle last year. I think it's almost 2 years ago. We went to Phoenix to a conference. That's where I got my degree from, right? So big family, very proud of every single one of them. And since this is a student seminar, I like to highlight the student success, right? So every single one of them are very successful in school and in research. And you guys are the reason why I do the things I do, okay? All right, next slide. All right, so since like I mentioned, I work in both CSETR and KEC. So the CSETR stuff I worked on, I did one seminar before when Dr. Chesa invited me. So this time, let me highlight the stuff I work with KEC. So as you know, KEC Center is a big center on additive manufacturing, right? Also, it has a lot to do with the stuff I am going to present today, right? So so there's many people there. I'm not going to go through the names. Just want to let you know I'm one of the faculty there, mainly working on ceramics and sensors. Now with a lot of collaboration with David S. Blaine, working on polymers. Next slide. Next one. Okay. All right. So here's a bit, I guess, a overarching slide to show what KEC Center does, right? So mainly we're looking at in situ monitoring and control. This is mainly on powder bed AM, especially metal AM. And the second column here is AM-enabled materials. We also synthesis materials, and then we synthesis polymer metals, ceramic composites, and then we use different methodology to do the AM. And then I am working in some area here as well. And the third column here is on hybrid AM. Mainly, we're trying to do embedded electronics. This is mainly driven by Dr. S. Plain, and we're trying to have electronics and wires, other components embedded in polymer components. So therefore, you're not only printing one material, you can printing material systems. And lastly is where my expertise initially comes to play. Mainly, we're working on ceramics, typically for functional ceramics for sensors such as Pierrot Electrics. And we also we're doing embedding sensings into a metal component using a stop-and-go process, as you see over here, of these fuel injector. And also we're doing a lot of coatings and metal matrix components as well. Next slide. Okay. All right. So now take more step forward into the details of what I do. So mainly, I'm working on these 4 different areas, right? I'll summarize everything together. So the top left is what we've been working on tabletop AM. Mainly, we are working on polymer composites, and with some ceramics. So uniqueness of the things we do is we synthesize these materials ourselves, and then we use 3D printing to print them. So we don't fully rely on these commercially available feedstock such as powders or filament. We make them ourselves, right? So the tabletop AM mainly we're using is FTM, direct write, select laser sintering, and the stereolithography. These 4 technologies are what we've been pioneering with. And at the top right, what you see here is powder bed AM. So mainly we're using bonder jetting and also select laser melting. At the same time, we're making bonder jetting printer ourselves in the lab, right? So Alexis is leading the effort on that. And what we're trying to do is we're trying to use these powder bed AM to make ceramics, especially functional, with functional gradient. So therefore, we can change from thermally conductive to thermally isolated materials. And in the same time, we're trying to do embedded sensors. We can stop the process in the middle, embedded sensors in component, and then we can have embedded sensing functionalities. Now, the lower left, what you see is multifunction composites. So our lab also pioneer in multifunction composites. We not only making carbon fiber composites, but at the same time, we are making these fibers that has a ceramic coatings on them. In the same time, you can embed these fibers with a polymer, so you can not only have mechanical strong, but in the same time, you can have embedded sensing, embedded damping in them, right? So there's lots of ceramic processing and manufacturing, such as powder, deposition, and the sintering process there. Lastly, to the lower right is what we're working on nano composites side. So we do a lot of material synthesis, like I said, right? So this picture to the second to the left is a carbon fiber with zinc oxide nanowires on them. So we use hydrothermal process to grow nanowires on these carbon fibers. So not only it increases its mechanical property, but in the same time, it's going to bring integrated embedded sensing or embedded damping process in them. And we're also making some graphene oxide in the lab using a wet chemical process. So using the high surface area, we can do quite a lot of interesting things there, such as energy storage. So there's lots of nano manufacturing, polymer process and manufacturing stuff there as well. So I know it's quite busy, but this is a slide summarize everything I do, and then hopefully that give you some ideas of what we are working on. Next slide. Okay, so the first thing I want to show you is the AM of polymer and polymer composites. Next slide. Okay. All right, so I have, I think, 65 slides total, so I'll go through, relatively speaking, fast. I'll give you some time to ask the questions, and we can have some discussions, okay? So first of all, the stuff we're working on is mainly on Pierrot Electrics, so they can be used for sensors, right? Some of you taking or retook my class on small materials, so you know these Pierrot Electric materials are ideal for sonars, for ultrasonic imaging, or for non-destructive evaluation, right? So the problem is they are ceramic in nature, so they are very brittle. Next slide. So the other type of Pierrot Electric materials, they are polymer. So they are, relatively speaking, flexible, and then you can bend it in. But the drawback is they have very low Pierrot Electric coupling coefficient. In other words, they are not that good in terms of Pierrot electricity compared to ceramics. So next slide. So what we're trying to do is we're trying to combine the best of both worlds, right? So here's how we did it. So we have barren tiny nanoparticles inside of a DMP solution. In the same time, this DMP will have PVDF powder, which is also piezoelectric. And then you can make a composite, has these barren tiny nanoparticles with the PVDF in them together. So we can make a filament, as you see over here in the middle. It's a black color filament that has common nanotubes, barren titanate, and also PVDF in them. So we're making this filament ourselves, then we loaded it into a most commonly seen 3D printer, FDM tabletop, right? So you can print it in the same time, you add a high voltage between the nozzle and the substrate, so you can align these dipoles in. So the key innovation stuff we're doing here is we not only made these filament, but in the same time, we did in situ polling, because this piezoelectric material requires high voltage to align the dipoles after the printing process. So we combine both processes into one. So as you see in the lower middle, so when you apply 10 Newton, 20 Newton, all the way to 80 Newton of force, you see the voltage response from the printed piezoelectric material is increasing, right? So the higher the voltage means the higher the force. So you can easily use that as a force sensor. Now, once you encapsulate them into a captain tape, when you bend it in or when you touch them, it gives you different voltage characteristics. So in other words, you can 3D print a pressure or touch sensors. That's what we pioneered. Next slide. Okay, so as a mechanical engineer by training, we not only care about sensings, right? We also care about mechanical property. So this is the thing I teach in class all the time, stress against strain, right? So as you know, the area underneath the stress strain curve is toughness. Basically, it's a measurement of how much energy you need to break the samples, right? So as you see, the brown color is PVDF, which is a polymer alone. So it breaks very easily. It broken at less than 50% of the strength, right? But what we find is once you add these ceramic particles, add these common nanotubes in them, not only give you sensing functionality, but in the same time, it increases the toughness by over 100 times. That's great, right? So you can not only make a material self-sensing, but in the same time, you can make it tougher, right? And the reason is because these nanoparticles, they are linking to the polymers, so they're basically kind of like an interlocking process. It's making the polymer tougher. And we also did dynamic testing that you see over here. So the PVD have long, they have low dynamic failure stress, but once you add these particles, it also can increase its dynamic failure strength. So that's good. So basically one stone, two birds, right? Not only you get a sensing, in the same time you increase mechanical property. Next slide. So we also did it one step further because we know these ceramics, they have dielectric property. In other words, it can store electrical energy. So once you measure the capacitance, you can back calculate the temperature. I'll just guide your attention to the picture in the middle top row. So you see the green line has 1.7 weight% of common nanotubes and 12 weight% of baryontinate. So with the increase of temperature on the x-axis, you can see the capacitance also increased. So basically, if you measure the capacitance, you can back calculate the temperature. So you have this embedded sensing for temperature as well. Next slide. So the other thing we've been working on is printing functional polymers, and especially for high temperature polymers, because polymer is great, right? But the problem is polymer melts usually less than 300 degrees C, right? So that really limits a lot of applications that you can use, especially in high temperature domains. So what we're pioneering is using these two different 3D printing technology, namely FDM and selective sintering, to print a polymer called a polyether ketone, or PEEK. So this PEEK will have a melting temperature above 420 degrees C. So that opens up a lot of opportunity for you to use this polymer for high temperature applications, such as for hypersonics, for these material requires for high temperature and high velocity applications. So what we're trying to do here, the uniqueness is we're mixing this PEEK with PA12, which is nylon, because most of these, like the sintering machines, they can only melt low temperature polymers because of the power limitation. However, we are using this PA12 as a binder to bind these PEEK powder together, and later on, once you go through the sintering process, you will have a PEEK structure. As you can see, it's lattice structurally designed and has lots of open pores, so therefore it can be lightweight and it can carry a lot of mechanical loadings. Next slide. So this is something I feel very interesting. I feel very proud of. This is what I did when I first came to UTEP. So what we trying to do here is combining shape and memory polymer with self-healing polymer as a biological inspired material systems. So here's how it works. So to the left, as you see, there's a fiber optic running through the polymer. And this is a special polymer. It not only have a shape and memory effect, but also has self-healing effect. So once a crack comes in, it's going to break that fiber optic. And then all the laser energy will be stored at the crack tip. It's going to heat up the polymer. Now, when the temperature increase, it's going to trigger the self-healing and the shape and memory effect. First of all, it's triggering the shape recovering effect. So it's going to close these gaps. And then later on, once you keep on heating it, it's going to trigger the self-healing effect. So therefore, it's going to heal it. So it's very similar as how our human body heals, right? For example, if you cut yourself too deep, the first thing you need to do is you need to go to stitches, right? So the stitches is going to close the wound, and then your body will slowly recover itself. So basically, this polymer system is combining the both effect. So it's not only going to close the crack, but at the same time it's going to heal itself. So these two charts here on the right is to show when you have virgin samples, which is black color, versus active toughening, you can increase toughness. And the lower right is to show like virgin samples with a toughened sample and a healed sample, you can increase the toughness of the polymer a lot, right? So therefore, right now, a couple of students in the lab, Jaime, they are working on using 3D printing to print these polymers. So therefore, the structure later on can be self-healable. Next slide. So next, I'll switch gears very quickly to show you additive manufacturing with small parts, basically a metal component with embedded sensors. Next slide. Quick overview, right? So as you know, most of the electricity are still generated by fossil energies, coal and natural gas, right? So I'm a firm believer of the diversify of all the energy sources. As you can see over here, there's a nuclear, coal, and a natural gas, and also renewable. Renewable energy is great, but the problem is, just like our investment, right? You cannot rely on one single energy source. You have to have the combination of all these energy sources to make it affordable and make it sustainable, right? But the problem is, of course, for the coal and natural gas, it's pollution, right? The pollution mainly is generated during the combustion process. So how do you control the combustion process accurately is going to lower the emission and lower the pollution a lot. So although the fossil energy is not good, but it's predicted it's going to be there, it's going to be here until 2040 or even beyond because of the diversification, right? Next slide. So the problem becomes, how do we control the combustion process? How do we lower the emission? How do we reduce pollution, right? So we need the sensors. As you see, this is a very harsh environment, so we need sensors to sense these conditions accurately, so therefore we could control the parameter accurately to lower the pollution, lower the emission, and then can make it better, right? Next slide. So I guess I used to have I had a video, but I don't think it's going to play because it's PDF. We can skip that. Next slide. Okay, so there you go. I took some screenshots here. So what we're trying to do is we're trying to embed a sensor in a metal component, so therefore can accurately sense the temperature, so can control the combustion process in real time. So the aim is to lower the emission and then lower the pollution. Okay, so here's what we did. We started with electron beam melting process. It's a layer by layer powder AM process. Probably you already know from Dr. Cesar Terrasa's presentation, right? So it's a powder bed, metal comes in using electron beam energy to melt the powder. So what we're trying to do is we're going to stop the process right in the middle. We manually embed a sensor, and then we'll finish the process. So therefore you can embed a sensor at any desired location as you want, right? So that's a key. Next slide. Okay, so here's what the process looks like. Initially, we just printed a cylinder to prove the concept, right? So we printed the bottom parts with the embedded sensor, as you see here, and then the sensor, what we're using is Pierrot Electric ceramics. So we're trying to sense temperature using its piezoelectric effect, and also potentially we can sense pressure by its piezoelectric effect. Next slide. One of the problems is when you embed a sensor into metal components or into any component, there's always trade-off, right? So it's really hard to get the best of both worlds, right? Once you embed a sensor, what are you losing? You're losing its mechanical properties. So this green line is basically you do a fabrication without interruption, and the blue is basically do stop and go. So you stop the fabrication, embed a sensor, and then finish your fabrication. What do you see here? You are lowering its ultimate tensile strength. You're lowering its Young's modulus, and also you're lowering its tensile strength. Because of stop and go, it cools everything down, and then it really halts the grain growth. So therefore, your material property at the interface is always bad, right? So what we did is once we put the printing back into the printer, we did a double scan. In other words, we scanned the interface twice. So therefore, that promotes the grain growth to continue to grow back. So therefore, you can see the red bar is showing the property gets increased a little, right? So therefore, we can somehow alleviate these issues. Next slide. Okay, this is a video. I guess it's not going to play. We can skip that. Okay, so here is what we did for Department of Energy, right? So they said, okay, cylinder is great, but can you make something that's useful? So we did a fuel injector, and it's 3D printed with embedded sensors, as you see, with sensor leads. So we use a stop and go to embed a Pierrot sensor near the flame front. Next slide. Okay. And one of the advantages of us 3D printing, of course, it's a rapid prototyping, right? So therefore, we have traditional machining using electro discharge machining, EDM. It costs us $6,000 in 2 months. But using the selective laser melting, it only costs us 25% the cost and also reduced into 2 days. So that's great, right? Next slide. Okay, so we showed it can be printed, right? But does it work? So here is it showing in a real testing environment, we have methane and air or oxygen gets combined. So you see the fuel injector is working. And in the same time, the sensor that's embedded in the component is working as well. So the top left is showing you the temperature sensed by the sensor compared with a thermocouple mounted right next to the sensor as a function of time. So you see the embedded sensor beautifully sense the temperature. It's very similar as thermocouple. So that means embedded sensor worked. It only survived the 3D printing process, but at the same time, it's accurately sensing the temperature. So next slide. Okay, so these are a couple things we did. I guess I'll skip that. So because for the sake of time, next slide. Next. There you go. Okay, so next I want to talk to you about these functional ceramics materials and components using 3D printing. Next slide. All right. So first of all, when I start to work with Keck Center, the center director, Dr. Wicker, always asks me, like, why you want to do 3D printing? My initial answer is, hey, I think it's cool, right? Everybody's talking about it. But he didn't like it. He asked me to go deeper, to think why we have to do 3D printing, right? So here's what my answers now, right? So, lots of ceramics are being used for sensors, for actuators, for different components. That's what we do, right? So these ceramics for sensors, actuators, typically they have custom geometries. For example, these are sensor joints that people use as a hip replacement. It is I guess personally tailored. Everybody has different shapes of bones, right? And then these Pierrot Electric tubes or semi-spherical shapes, they are used for saunas. So they're also custom designed, right? So the shapes of these ceramics has to be different for different applications. Or the scanning heads for ultrasound imaging, or for those they used in gas turbines as coatings. These has to be custom designed. So it's very, very hard to make them because when you make a ceramics, 80% of cost can go to machining, can go to post-processing. So if you can print them and somehow make a near net shaped ceramics, that can not only reduce the cost by 80%, but in the same time, it can accelerate the fabrication process, right? So in the same time, because 3D printing, you can have a functional gradient. You can have metals and then ceramics and then metals again. So you can have these functional gradient materials that no traditional manufacturer can do, right? And again, lastly, these multi-materials such as ceramic matrix composites is getting a lot of attention. So therefore, you can not only get a high temperature property of ceramics, but at the same time, you can get ductility of metals. So that's what 3D printing can play. That's what 3D printing's niche is. Next slide. Of course, everything is easy said than done, right? So as you guys all know, 3D printing of polymer is everywhere. You can even buy a polymer printer at a Home Depot, even Walmart.com for like $500, right? Metal AM is everywhere. You see at a Keck, there are lots of metal AM machines. But why not many ceramics AM yet? The problem is because ceramic AM is very hard to do. And then the reason is because of this. All the ceramic AM, they're indirect additive manufacturing. In other words, we are printing the polymer, you're using photopolymer or you're using slurries to print it now using direct write. Later on, you have to do a process called sintering to solidify the ceramics. So how do you predict the geometry after the sintering process? How do you predict the distortion of the geometry after sintering? It's very hard. In other words, printing polymer and metals, whatever you print is whatever you get, right? But for ceramics, it's not, because you have to bring down the polymer binders, and then you have to solidify ceramics. It's going to shrink, it's going to distort. So it's hard to predict what does it look like, right? So therefore, we try to pioneer in the modeling of post-processing, so you can predict the final geometries. So during design, you can compensate for the distortion and compensate for the shrinkage of the dimensions. And then also, of course, there's lots of hybrid AM, multi-materials that you can do for ceramics AMs. And then lastly, because of the nature of defects showing in the ceramics, really we have to do a lot of calculations to determine the internal defects, so therefore you can predict the material properties of the ceramics again. Next slide. Okay, so here's some of the things we are pioneering in the lab. So mainly there's 3 different kinds of methodology you can use for 3D printing of ceramics. The first one to the left is direct write. So it's either using pneumatic or piston, or basically, just using the electrical force to drive the motors, right? So this is an easy process. This is how ceramics are typically made. So you make a mixed ceramic with polymers, and then you extrude them out, kind of like push the toothpaste out, right? And later on, you sinter it. And then the one in the middle is powder bed, using select like the sintering or binder jetting printing. So you have a ceramic powder at the powder bed, and you shoot out either using laser energy or using polymer binders to bind them together. And then you sinter them at the end, right? And then the one to the right is mostly commercially available or successful printers that's focused on based on photopolymers, using stereolithography and direct digital light projection, right? So this is basically mixing these polymer with ceramic nanoparticles, and then you can solidify the photopolymer. Later on, you do sintering process to burn that out. And then there's also a new technology called material jetting, right? So with ceramic nanoparticles and polymers through these similar as inkjet printing heads, and you can shoot that out using supporting structures, and then you also need to go through sintering process to print it. So there's no typical winner at this moment. If I'll say which one's best, probably the DLP and SLA. This is mostly commercially available, right? So there's a pros and cons for each one. I'm not going to read the details. You guys can read it yourself, right? Mainly the density and mainly the resolution are different, right? So for us as a researcher, we want to look into every single one, because none of them is going to solve the problem, solve all the problems. Okay, next slide. All right, so I'll give you some overview slides of what we do as ceramic again, right? First of all, the binder jetting. Next slide. So what we did here is we start with alumina. As we know, alumina is pretty much the most commonly used ceramics, right? So all the ceramic tubes you guys use for sintering or the high temperature isolation materials, a lot of them are based on alumina, right? So we printed it in, we did the sintering, and we can print the different geometries. As you see over here, what we're showing here is after sintering, we can increase the compressive strength about double, right? So that's good. Next slide. And the other thing we're doing is we're doing binder jetting printing of barium titanate, which is a Pierrot Electrics ceramic. So what we're showing here is we can control the geometry of the printed ceramics. As you see to the right image, not only we can control the lattice density, but we can also have porosity control as well. And then we can later on, once you do the sintering process, we do the polling process to measure its Pierrot electric property. Next slide. Okay, so what we're showing here is we measured its dielectric and the Pierrot electric property. In other words, to measure how good of a sensor it is, right? So what we're showing here is, by the way, you electrode them differently, either on top and bottom or left or right after you printed them, we can control the dielectric and the Pierrot electric coupling coefficient. In other words, we can control the way you use it as a sensor, either sensitive to pressure or sensitive to temperature. Next slide. All right, so the other thing we did is we're looking at particle size control, because one of the things, for powder bed, how do you make a good powder bed is very important. That's probably the most important factor in terms of controlling the final property, right? So most of the time you have to use spherical particles. You have to use biparticle size distribution to give you high density of powder bed, right? So we're studying that to print these thing called PZT, which is the most widely used Pierrot electric materials out there. And we showed we can get about 80% of the theoretical value by using this morphology control. Next slide. All right, so the next I'll show you some direct write, right? That's another technology about printing ceramics. Next slide. Okay, so we started with preparing the slurry. In this case, you're just mixing these ceramic particles, in this case nanoparticles, with polyvinyl alcohol, which is polymer, and you add water in, then you can make a slurry, very similar as your toothpaste, but probably more viscous. And then once you go through a syringe, you can print that out, either a cylindrical shape or a square shape. That's pretty easy to do, right? So what we find here is this density, it is a function of a particle size. So the yellow here is theoretical value, and a blue, orange, and a gray 100, 300, and 500 nanometer particles. So here, what we're seeing is these 100 nanometer ceramic particle give you the best density and the best piezoelectric coupling coefficient and the best dielectric constant. The reason is because the smaller the particle it is in nanometer scale, the higher surface energy you'll have, so the better it'll sinter. So this is a very interesting to see, because you want to have a high density, so therefore that give you better mechanical, electrical, and dielectric properties, right? This is exactly what we're seeing here. Next slide. Okay, so this is just an SEM picture to show you, right? Obviously, 100 nanometer particle give you less defects, right? So that's why we're seeing better mechanical, better dielectric and piezoelectric properties. Next slide. All right, so the other thing is we don't want to print just a bulk ceramics, right? We want to use the design freedom of 3D printing. So what we're showing here is we can control the processes. Not only we can printing the lattice by varying the density from bottom to top. At the same time, we can add these polymers, which is a polymer, right? During the sintering process, it gets bent away, so therefore you have the porosity in it, as you can see in the lower right image. So why do we do that? Because the higher porosity you have, the lower impedance it'll have, or higher surface area it'll have. So they better sensitivity, give you better sensing capabilities, right? So controlling porosity, controlling lattice, give you better sensing capabilities. In other words, next slide. All right, so this one here is just to show you. Again, we want to printing some PZT, which is the most useful piezoelectric ceramics, right? So what we're seeing here is we can achieve about 95% of theoretical density, which is very good, right? Achieve piezoelectric and a dielectric property that's even better than commercial value because of the carbon residues, right? So basically, once you do slurry printing, sometimes these carbon residue after sintering is not good for you, but in this case, it's better because it forms a lot of local small microcapacitors to increase the dielectric and the piezoelectric property. Next slide. Okay, so this is one summarized slides to show you we can print in different geometries, different shapes for different applications, printing ceramics with Interact Right. Next slide. Okay, so this is another interesting application. So we were able to print alumina and control the lattice structures. So therefore, we can use it for humidity sensors. So the higher the surface area, like I said, the higher sensitivity it'll have. So basically, you can print a humidity sensor based on the lattice, based on lattice design, use 3D printing. Next slide. Okay, so this is an interesting thing we're trying to do. So as you see, we do a lot of hands-on experimental work, right? A lot of times we're just doing trial and error. So we're trying to have some modeling to control these or to guide these experimental process, right? So one of the things we did is we're looking at particle size distribution, controlling the properties, right? So as we know, if you use bimodal particle distribution, it gives you the best packing density. But after sintering, it's a different case. So as you see, the orange here shows you where you have two different particle size. When you mix them, the highest density is roughly 0.35, right? When you mix big with small particles. However, after sintering, let's show the blue over here, top right. So the small particle, in this case, is 100 nanometer, give you better density. That's because of the high surface area it has, high surface energy during sintering. So therefore, it really depends on what you want to do, right? If you want to have a good green body density, then probably you have to mix these particles together. But if you want to have a good final density after sintering, you want to use more small particles because small particles always sinter better than big particles, right? This is what we learned, and this is what we find. We're in the middle of getting this thing published. Next slide. Okay, so the next few slides, I want to show you multifunctional composites manufacturing. Next slide. Okay, so the thing is, what inspires us is composites are pretty much everywhere, right? So people use it for airplanes, for submarines, for ships, even for racing cars, right? But how do we add these functionality into it? That's going to be great, because oftentimes, just like a human body, your body not only protects you from external environment, but also, you can sense heat, you can sense pain, you can sense a cold, right? So all these sensors are embedded inside your body. So that really can help you to simplify the structure, but also can help you lower the weight. One of the good example is the solar cell airplanes here you see developed by NASA, right? So this entire airplane wing is a solar cell. So not only give you aerodynamic to give you lift, but at the same time give you power, right? So that's what inspires us. Next slide. So what we're trying to do is we're trying to do coatings of Pierrot Electric materials on carbon fibers to make them not only mechanically strong, but at the same time, you can have some embedded sensing in them. Next slide. Some modeling, right? Some equations. I know nobody likes equations. I'll be brief, right? Basically telling you by controlling the coating thickness, you can control the Young's modulus, you can control the Pierrot Electric response. Next slide. Okay, so this is how we make them. So this is an interesting process. You have these nanoceramic particles and you disperse them in organic solutions. Once you apply DC current, all these particles will deposit onto the cathode. And then once you do the sintering, you have a ceramic coating of on the outside of these fibers you use. And then you can do post-processing to make them Pierrot Electric. Next slide. So basically, here's what we're trying to characterize. It's dielectric energy storage, and it's a sensing capability using IEFN. So basically shows it worked, right? It matched well with modeling. Next slide. Okay, so the other thing we've been working on is doing some chemistries to the fibers, right? So as you know, a lot of fibers, especially biofibers, they are very rough on surface. So the top left figure you see is a collagen network with muscle fibers. And you see how rough the surface is, right? It's because, the rougher the surface it is, the more interaction of the fiber and matrix it'll have. So that give you better load transfer capability, right? So what we're trying to do is we're growing these zinc oxide nanowires on the outside surface of a carbon fiber in order to increase its load transfer capability. Next slide. Okay, so this is how we make them. This is very similar as how you cook your dinner, right? So you add solutions, heat it up, and then it's going to grow nanowire. Very easy, very simple, right? You can scale it up to 10 meters long, continuous fibers. Next slide. Okay, so the first thing we characterize is to see whether it works or not, right? So we just want to bring your attention to the blue and the red lines here, right? So the blue line is with the nanowire interface, the red line is without. So you see the number of fragmentation inside this fiber is more. So the take-home message is the more fragmentations means the more loading is being transferred from matrix to the fiber. So that means with nanowire it is way better, right? So that's good. Next slide. So we also scaled it up, make a V0 shear testing. These solid lines here is to show increase of shear modulus and shear strength. And these all the dotted lines are the ones without any nanowires, so therefore shows less property. So that basically what you're seeing here is with the nano interface, it increased mechanical property of these composites. So that's great. Next slide. Okay, so the last topic I want to cover here is nano composites manufacturing. Next slide. So like I said, we make a lot of nanomaterials, right? So this is some of the things we made in the lab. We made a high dielectric ceramic nanowires. So what we did is we mixed them with polymer. Now we're in the middle of using direct wire 3D printing to print them. So therefore you can align these nanowires to increase its dielectric property. Next slide. And again, people will ask like, why do you align them, right? So the reason is because all these nanomaterials, they're orthotropic in nature. In other words, in longitudinal property, the mechanical property or the electrical property is way better than the transfers. So once you align them, these property overall is going to be better in the longitudinal direction. Next slide. Okay, so we also use the wet chemical process to make a lot of graphene oxide. So some of you guys might heard of graphene oxide. It drew a lot of attention about 10 years ago, right? Still quite a lot of attention because of the excellent mechanical thermoelectrical property. So we can make a graphene oxide aerogels in our lab. Looks like a sponge. Next slide. So what we're using then is we're using its high surface area for batteries, right? So as you know, the problem with battery is the amount of energy it can store and how fast the energy can be stored, right? So we use a high surface area to not only reduce the charging time, but also increase the capacity. So this is what you see here. I'll just bring your attention to the lower right. So the number of cycles versus specific capacity. With the nanowires, not only it maintained the capacity, but in the same time, it's lowering its charge and discharge time. So that's great. Next slide. This is the other thing we're showing using these nanowire and the carbon structure for supercapacitors, right? So one of the things people use capacitor is to release energy quickly, right? For example, flashlight, or for example, in some cases, you want to release energy quickly to give you more energy density, right? So it shows with this architecture of nanowire in micrometer fibers give you better charge and discharge capability as well for energy storage. Next slide. Okay, so there's some conclusions, right? So mainly we do a lot of material synthesis for advanced manufacturing, right? So you see we not only synthesis material, but we can combine them with tabletop or powder bed AN, and there's lots of interesting things we do, but we're focusing on functional materials for energy storage, for sensors, for other things, right? And what we believe is by sitting in the interface of material science, mechanical engineering, and advanced manufacturing, there's lots of things we can do, right? Lots of functionalities, embedded sensing, self-healing, thermal management, energy storage, actuations, those things, right? So ultimately, we want to make a material system that's smart, that's similar to our human bodies, right? You can have embedded sensings, you can have self-healings, and you can be adaptive. That's what we want to do, right? And advanced manufacturing is a key part of enabling this stuff, right? Because you don't want to have material that's only available in the lab. You want to bring it up to be upscaling and advanced manufacturing, especially 3D printing. I think that's a key to enabling the large application of these materials. Next slide. All right, so lastly, I want to have an acknowledgement slide. Of course, these funding support from DOE and SF and especially NSA, right? And also Department of Education. And most importantly, all the students. This is an old picture we took last year, and we were going to take a picture, but you guys know, right? It's not ideal, right? Outside right now. So these are students, they work days and night in the lab. I did all the things. I don't do anything, right? All I do is just, stand behind a computer and talk like what I'm doing now, right? So I'm very proud of every single one of them. I'm not going to, say their names out individually. A lot of them graduated. They're working in a lot of different places, in national labs, in companies, right? And some of them have become faculties as well. So the other one motivates me, and the other one doing all the work, right? I guess still have a couple minutes, maybe. Yeah. So we can open up for questions.
I have a question, Dr. Lin, that a lot of students typically ask. So one of them is, one, where can they apply to work with you on these projects? And two, what are the requirements?
Okay. So I guess the short answer is usually require GPA 3.0 and above, right? And some project requires US citizenship, but about most of it does not. So therefore, if you guys are interested in working in my group, I would ask you send an email to those PhD students who's leading the effort, right? So we work in groups. Right now, there's 5 different groups working on 5 different things. As you see, we're doing a lot of different things, right? So the PhD student is leading the effort, and I usually ask you guys to send email to those PhD students, and they will interview you, and they are the one actually hiring students for us. Yeah, so. But I have limited position at this moment because I just hired 4 new students. So, but if you're interested, feel free to send an email to my PhD student. I can totally give you the email address, and we can go from there. Any other questions?
Dr. Lin, good afternoon. I'm Khan speaking.
Hey, Khan.
Hey, how are you?
How are you?
Yeah, fine, thank you. I'm curious, one point, you are working on the many materials, metamaterials, advanced materials, etc., etc. So how much you are involved with the electrical properties characteristics and their degradation in space environment?
Yeah, that's a very good question. So I think for this electrical property, what we typically measure is its dielectric and electrical conductivity. And in terms of degradation, we don't do any degradation testing yet. But I'm in the middle of collaborating with Dr. Stewart. He does this accelerate testing using temperature, pressure, all combined, right? So we are trying to measure its dielectric electrical conductivity before and after. So that's how we characterize it. And in the same time, I know there's a micro CT, those things, right? They can look at internal defects with the degradation depends on different radiations or temperature. So yeah, so if you're interested in, we can totally working on something together.
Yeah, I'm very interested because you are working very fundamental works and you study the properties of the materials when they are incorporating different types of materials. So I'm really, really very interested. And if you give me some time, we can talk sometimes to, it may take around 10 to 15 or maybe 1 hour. So we can cook something if you allow me to talk.
Okay, totally.
Okay, thank you very much. Thank you.
If anyone else has questions for Dr. Lin, feel free to type them in the chat or raise your hand.
All right, I guess no question. You guys had it easy. I mean, very good. Everybody's hungry and ready for lunch, right?
Awesome. Well, thank you so much for your time, Dr. Lin. It was very informative. I don't know how you do so much, but I'm very lucky that we have you in this department. And, you know, if anyone else has any questions, you can always send them to me and I'll refer them to Dr. Lin in the future. But for now, I think we're going to close out this session. Like I said, it will be posted to YouTube either tonight or tomorrow. And we do have one question, Dr. Lin. So if they should email your PhD students, what are their emails?
Okay, so if you want, I can type the email address here in the chat box. Is that okay?
Perfect.
Okay. All right. Sounds good. Well, I guess if no more questions, enjoy the rest of your day. Right. Thank you for calling in and take care. Be safe.
Thank you, Dr. Lin.
Thank you. Bye-bye.